Hello, yeah, my name's Stefan Krawczyk. I'm excited to talk to you today about an open source project I created at Stitch Fix. And effectively, one of the things that I want to leave you with is that, if you use it, you're going to get software engineering best practices are going to come for free. In terms of how I find myself here, so I've been in Silicon Valley since 2007, been at a bunch of places. Most famously, I was at Stitch Fix for about 6 years, where I was on the platform team helping over 100 data scientists prototype, productionize, and then be on call for what they plug back into the business. That's where kind of Hamilton created it, open sourced it, and then I decided to start a company around it called DagWorks. So on to the talk. So in terms of, slightly rhetorical question for you all, since you're probably here and you probably, value this already, but, why should we care about software engineering principles, right? What would you think of, what would you say to your CEO if they came up to you and asked, why should you care? To me, the reason to care is that it helps amplify and scale your kind of human efforts, right? Since generally in a company, we're one of the most expensive people there, and so in which case, if we can, write code in a way that we can move faster, right, then the business will get more value out of us, right? And so this is, where I see software engineering principles, playing into business value. So in terms of this talk, right, I'm just going to give you a story of motivating pain, why we created Hamilton. I'm going to explain what Hamilton is, give you a brief mental picture of some general usage, and then talk about the native software engineering practices that I think Hamilton kind of gives you for free if you use it, and then summarize things. So context-wise, motivating pain, right? At Stitch Fix, there was a data science team, one of the oldest in there, that had to provide operational forecasts for the business. The business basically had to make decisions based on their numbers. So how many warehouse workers should there be? How many stylists should be staffed? They basically were always under the gun to produce numbers. And so this meant every week, every month, they had to adjust to a constantly changing world and answer to questions that an exec team might have as to what's going to happen with the business, so we can know what to do. Their flow looked like something like the following, right? But in terms of iteration and getting things out, their biggest problem was creating this featureized data frame. And so this is what Hamilton was set out to solve. To give you a bit of a grounding in a sense for what the problem was, right? So I'm just going to walk you through a script. So the script basically looks something like the following, right? It loaded some data from some databases, say the amount of marketing spend, the number of users signed up. They then would add columns to this table. Features is another way to look at it, right? Maybe this was conditional based on some logic, so there would be some branching. Then maybe they would have some one-line incantations, and then maybe they would also delegate to a bunch of functions to add features to this data frame that then they would save and then go fit a model. You might be asking to me now, what's the problem here? This code looks pretty normal. This is how I write things, right? But picture the passage of time. Different people, years going by, and invariably with data work, you're always adding, not removing. So inherently, you're trying to make things more sophisticated, and so things get more complex. And so if you write code in this way, like the maintenance and update and iteration cycle, right, for them was tough, right? This code doesn't have a great unit testing or integration testing story. Where do you put the unit tests? You have to think write code from the beginning to make it work well. Integration testing is tough. You need to run everything to get something. And then this impacts your data quality, since there's a problem, like where did it come from, right? And then if you're onboarding someone or bringing someone new, right, this wall of text is kind of intimidating. Maybe there is some special constants or numbers. How do you document it? There isn't kind of a standard way to kind of do it. And then in terms of as the script grew and things start to depend on each other, right, you wouldn't know that dependency unless you inherently knew and read the script, top to bottom, right? And so tracing, being able to be confident in making a change and not knowing you didn't break anything basically meant you had to understand a lot. And then invariably with data work, you're iterating and you're generally doing small perturbations on what existed before. When you write code in this kind of a style, right, if you want to reuse some definitions, the easiest thing for a data scientist is to go and cut and paste rather than go refactor. So then you have this problem of propagation of definitions and other kind of problems that come about of having a lot of the same code in different places. And so then this impacted the team, how quickly it was able to onboard someone, and then also subsequently how fast they were able to debug something if there was an issue. So suffice to say, I don't think this problem is unique just to Stitch Fix or to anyone, or to even to their particular time series forecasting problem. So make sure I haven't put you all to sleep. Does anyone relate to these problems? Or yeah, I've got a few hands. Would anyone want to inherit code that was written like that? No hands, good, yeah. Independently, would you be in anguish if you suddenly had to inherit your colleague's code? Anyone? No? Yeah? So this is kind of what I think, some of the requirements we got as to like what we wanted to build Hamilton for to help solve, right? So what is Hamilton? Sorry, I'm skipped ahead. Yeah, so what is Hamilton? In one sentence, it's a micro-orchestration framework for defining data flows. We write declarative functions. I'll get into this, but you get a lot of software engineering best practices for free. The point here is it's also a library, so it's very lightweight. You can pip install, get on your way very quickly. And if you're bored of me, you can go to tryhamilton.dev and go and play with Hamilton in your browser right now. So let me unpack that sentence. So what do I mean by micro-orchestration versus, well, the contra is macro, right? Macro-orchestration is about, something like what you use Airflow for example, is about orchestrating an entire flow end-to-end where you're sequencing different computational tasks one after the other. Micro-orchestration is, I think, handling the code within a particular step, right? So really focusing on one step, and so that's kind of where Hamilton's roots are, right? Focusing on this inner step. And so then what's a data flow, right? It's just a fancy way of saying how data and computation flow, right? And effectively in computer science terms, this means you can express it as a directed acyclic graph or DAG. So this code I showed you before, this procedural code, is in fact a data flow, right? And that's because you can express it as a directed acyclic graph. All right, and you can see here that spend is required to compute average 3-week spend, right? And then it's also required to compute spend standard deviation, right? And so you can kind of map this procedural code into a data flow. And so that's really what Hamilton is really trying to help orchestrate, right, is this kind of code. So what do I mean by declarative functions? Well, effectively, when you read the function, it declares what you can create, what you can get out, and then it also declares the dependencies that are required for computation. Now, you don't run these functions directly, but the key is that if you read the function, you'll understand what it does, what it needs. The reason I kind of, this paradigm kind of came about was, the problem was that given, I'm sure all of you had to debug some, data frame or table of an output. Part of the task of that is to understand, hey, for this column, what is the code that you, transformed it or created it, right? That's generally pretty difficult. So the idea was, can we make this as easy as possible? So given an output, say in a data frame or given a column, can we make that column, what created that column, map to exactly one Python function? And so then the idea was, okay, given that can we map it to one function, can we also determine, the dependencies from how it was written? So I'll show you this on the next slide, but in Hamilton, right, the output, something you can get, is determined by the name of the function, and the dependencies are determined by the input parameters to that function. So in the Hamilton paradigm, instead of writing this procedural code here, so this is Pandas code, which I assume you're familiar with, instead of assigning two columns C and D, kind of in this procedural style, you instead would declare them as two functions, C and D. All right, so C and D are two things we can output, so they map to function names, and then the input function input arguments map to the input parameters to these functions. So for C, we only require A and B, so that's why it's declared, and then for D, only C is required. And then you use the Python body for whatever Python code you kind of want. And so, but you don't run those functions directly. So a full hello world kind of looks like the following, right? You describe, you put your Hamilton functions into modules, and then what you need is some driver code to kind of execute it. The point of the driver code is to import, the Hamilton module, but also to import this feature logic module here. The real magic happens when you pass it to the Hamilton driver. And so what it's doing under the hood here is, given some configuration and whatever modules you pass in, it is crawling the modules past and effectively doing graph theory 101. So if we can find a function, it's going to create a node, and then it's going to use the function input arguments to then define edges. So you can see here on the right, from these two functions, we have a pretty small graph here where A and B are inputs, and then C and D are two functions. And the reason why A and B are inputs is because Hamilton didn't find another function definition that mapped to them. So then it assumes that they must come from input. And so then once you've kind of given this graph, right, you can then tell Hamilton or ask Hamilton to compute something, and then Hamilton will only walk that part of the graph to compute a result. So you can end up building a very large superset of possible things you could compute, but Hamilton will smartly only compute the things that are required for the output you wanted. The examples I'm going to show here are going to be, pandas-centric, but just to point that Hamilton doesn't care what Python object type you're operating over. It could be polars, could be NumPy arrays, could be your custom object type, and so it's pretty flexible and extensible. Some other things I'm going to mention, but I won't cover, is that you write functions, but you can also decorate them. And Hamilton has a rich kind of set of things you could decorate things with. So add more metadata. You can parameterize functions. You can have syntactic sugar to extract things. You can add runtime data quality checks. Conditionally, include functions or not, and then even parameterize different parts of your subdag. And then more so, I won't talk more about this, but Hamilton's portable, right? Runs anywhere that Python runs. And so and it also has hooks to scale. So it has plugins for PySpark, Ray, and Dask. And you can use it in DBT to Fast API to your Jupyter Notebook. And so, I will refer you to the documentation to know more, but just to plant that. So just to complete the circle at Stitch Fix, right? So Stitch Fix Hamilton has been running in production since 2019. So the team before Hamilton was only managing about 1,000 kind of feature transforms, but afterwards they kind of grew to easily managing over 4,000, right? And adding more of these feature transform definitions did not slow the team down. And so the teams that Stitch Fix used it loved it. And so the anecdote is at Stitch Fix, one of the teams used to take them a day to update features, fit a new model, and be confident that they didn't break anything. They used to take on the order of a day, and then it took less than 2 hours with Hamilton. And all we did was just change what code they need to change, update, and be confident to getting your forecast out. Subsequently, it also meant that we found out, it was faster to onboard team members because they had lineage and documentation, code reviews were faster, and then they finally had, unit tests, and then also the ability to expose documentation via Sphinx. And so if you want to adopt Hamilton, you wouldn't be the first. It's been, since we open sourced the project, there's a bunch of people who've kind of been using it in production. So, but otherwise, since I started the company DagWorks, we had to fork the repo, so that's why there's two, but there isn't any schism or anything where we're the main caretakers. Cool. So just to give you a little bit of a mental picture of what a Hamilton project kind of looks like, right, is that, it's very general purpose. And so the only real requirement is that if you can draw a flowchart or a decorated acyclic graph, you can put it into Hamilton. So feature engineering classically is a great use case, right? Maybe if you're doing just regular Python data processing, right, you can kind of transform your scripts and rewrite them to Hamilton. You can express end-to-end machine learning pipelines, MLOps integrations. You can even use it in a web request. So people are using it in Fast API to manage the web request stuff. And then you can even use it in place of LangChain. And if you're a software enthusiast, right, you'll probably like Hamilton because it helps your code look more structured and reduces your code complexity. In terms of the structure of a project, right, with Hamilton, say a classic example, feature engineering, as I mentioned, the thing to kind of note is that with Hamilton, you end up writing modules, right? And so if you want to do feature engineering, you generally end up, thematically kind of grouping functions that, load data, and then, transforming functions that use the outputs of the data that's loaded to kind of, transform it. And then you're then going to be writing what we call drivers that then kind of help, materialize a result. The point being that for each driver, right, that couples context, it will only kind of walk the graph for what's required from that particular output. But from a code-based perspective, high level, a natural structure kind of emerges, which I'll kind of touch on in a few more slides. But effectively, what Hamilton helps you separate is logic from execution context, which is a very useful property for the longevity of good projects. Cool. So on to native software engineering best practices. Here are 5 common ideals, right? I think trying to assess software engineering best practices is a little kind of subjective, right? And so here I've kind of picked 5 common things. So who here knows all the acronyms that are on the slides? A few people, no, kind of, right? Don't worry, I'm not going to go through all of them because I think there's a bit of overlap between them. But KISS is for keep it simple, stupid. YAGNI is you aren't going to need it, so don't over-engineer things. Dry means don't repeat yourself. And then solid, which comes from for those of you who've done object-oriented Java might know it, but I'm going to take my my interpretation of it and compare how Hamilton fulfills it. Cool. All right. So I think testing and documentation are pretty much I think when people think good software engineering best practices, these are the first 2 things that people kind of reach for to say this is what you need to have, right? And so I think with Hamilton this is pretty easy, right? You can give this to a junior data scientist, they can write functions, and magically the code is always unit testable, right? Why? It's because you force people to write these functions, and because they're declarative, right? You're forced to not actually include too much in the function itself, and so this means that it's very easy to kind of write a unit test that then passes just the things in to test the logic that you want. In terms of, if you want, if you're doing data work, it's also very important to try to add, expectations on data, right? And so Hamilton, if you're familiar with the term shift left, has shift left to the extreme. It allows you to not only have the function definition, right, but then also actually set an expectation that will run at runtime that you can, log a warning or pass or fail based introspecting the output of a function. If you're familiar with a library called Pandera, if not, I highly recommend you check it out. Hamilton also has integration with that. And then, you read code more often than you write it, right? And so, documentation is usually a bit of a chore, something that tacks on, right? But I think with Hamilton, it's kind of part of the way that you end up writing code. And so, because of the way that you're forced to name things, as a function's names are supposed to mean something, that kind of propagates through your code base. So you might have things that are a little more verbose, but in some sense, they're actually then much easier to read and understand. And then, of course, you have the doc string of a function to add more documentation. Hamilton does allow you to add more annotations. And so all this kind of information is all accessible once you build a graph, right? You can actually access these tags on things to do some pretty cool stuff. And then, as I'll show you on another slide, you can actually visualize everything pretty easily with Hamilton. And so suffice to say, with just these 2 things, you have a pretty strong base to kind of scale your team and code, right? But it's not going to, as I'll show you in a second, like a code that's easily testable and documentation friendly doesn't generally also mean that you can move very quickly. More on that in a bit. But as I mentioned, Hamilton has this visualization capability, right? Every function you write effectively can map pretty easily to a node in this kind of graph. And so this means if you ever want to, if you've ever drawn something like this by hand, of going through a code base to understand how everything connects, well, with Hamilton, it's in Hamilton, you get that for free, right? And this means that you can always have up-to-date documentation. So when someone changes a particular graph, it's very easy then to go visualize it. The flip side of this is you also get lineage as code. So if you connect Hamilton up with your Git repository system, you can encode this graph, right? And so you always then, as long as you know what git commit SHA you kind of produce an artifact or a data frame with, you can always go back in time and understand, the lineage, so to speak, as to how things were computed. And so just to compare to the code from earlier, right? This code, I think, struggles to embody easy testing, documentation, and visualization. And so in which case, I think, Hamilton is a great step above. So let me show you, how Hamilton even goes further, right? And how it can actually help you with more of your software development lifecycle by imbuing some pretty good software engineering principles. So to kind of, the thing that I kind of ask you to think about is, think about your code base. And the things that I'm going to go through, think about how does your code compare, or how easy and fast would it be for you to change or modify things. So SOLID, for those who don't know, comes from object-oriented days. It's an acronym. I'll walk through it in a sec. But essentially, the ethos or the thinking behind it was that if you follow these principles, you'll get more value out of the work that you're doing because it'll be easy to change, manage, and update, right? And so I'm going to kind of take liberty and interpret this, but applied to data flows, since we're not doing object-oriented kind of work here. But I think the ethos or the thinking behind it is very applicable, right? Since we have to change and update our data flows, since it's not just getting to production once, it's like how do we evolve the code, right? So S stands for single responsibility principle. The idea is that code should really only do one thing. And the reason why is that if code only does one thing, right, it's just easier to test, maintain, manage, and change, right? And so with Hamilton, right, you're forced to kind of do that with your function definitions, is that the function does one thing, right? It's a one named thing that you kind of create, right? So then if I want to change, for example, what embedding means, there's only a single place there, and it's very clear who's using it or consuming it, etc. From a business logic standpoint, that's what these functions do. But I also want to point out with the driver that you get with Hamilton, isn't coupled to any of this business logic that it kind of runs. All its purpose is to handle context of what and where. And so this net result means that you have, execution is decoupled from logic. And so this then means that it's easier to test, maintain, and change. And this is, I think, a nice embodiment of the single responsibility principle. O stands for open and closed principle. The high level is that things should be easy to extend. So existing code, you should be able to use it and extend it, but then hard to break. And so the idea is that you should be able to prevent issues from happening with code evolution. I have defined here a data flow. So LLMs are hot. So I have two functions, one called embedding that computes an embedding from OpenAI. That then is fed, and I have another function, nearest neighbor IDs, that takes an embedding VectorDB client and then computes, tries to find the nearest results given this embedding. If I want to extend, right, I don't have to go in and modify an object-oriented hierarchy. I don't need to go modify a script. I just need somewhere in the world where I can pass this to the driver is a function that just depends on the things that I want. So if I want to extend and use nearest neighbor IDs, all I need to do is write a new function that takes nearest neighbor IDs as an input argument, and then I have now easily and quickly extended existing capabilities without too much software engineering work. In terms of hard to break, right, Hamilton gives you a lot of a lot of layers that you could add in to make this true. And so when you write functions with Hamilton, Hamilton does a check on kind of type annotation, so that if someone is consuming height zero mean unit variance, they should expect a pandas series. And then if you are trying to run this function, Hamilton will complain, hey, if you have not satisfied and provided an input for an output that you want. And then, as I mentioned earlier, you can also add runtime data quality checks, so you can even further ensure that logic and the expectations are in sync. And then, as mentioned previously, it's easy to unit test, and then integration testing is also pretty straightforward. A lot of things that people do, one way that people make use of this is actually in CI systems. It's very easy in Hamilton to just compute a single path of your graph, and so if that's something very important to you, very easy to kind of add that into your CI system and just compute the path that's important to you. So this then means that if someone else is going to change something, it's hard to kind of break things without knowing it. L stands for Liskov substitution principle, named after, I think, a lady called Barbara Liskov. The high level is that it should be easy to swap parts of the flow without altering its correctness. And so here I have an end-to-end machine learning kind of pipeline, right? The boxes here correspond to 3 modules that kind of define, data loading, feature transformation, and then kind of model fitting. In terms of, Hamilton gives you a few interpretations of swap, right? This code here is very easy. We haven't, the logic here, if we wanted to run this in a web service or in Jupyter, right, there isn't anything inherent that we have encoded here to stop us from doing it, so it's very easy to swap where code runs. In terms of modules, right, Hamilton makes it, in terms of, if I had, in development, I load data differently from production. I can very easily, swap out this data loading module for, how I load it in dev versus prod, and the correctness of the program will continue to flow as long as I have, created the right kind of function definitions that then the rest of the pipeline depends on. And then in terms of if you don't want to swap out modules, you can also swap out functions very easily, right? And so, say I wanted to extend the example before, but add in, support for Anthropic. We can actually very easily, with some simple augmentation and this kind of @config when annotation, conditionally swap out a function implementation very surgically, and then anyone downstream of that is none the wiser, since they only, depend on, the name of the function. So the input parameter, and as long as that's satisfied, it's very easy to kind of swap in different implementations. So since I only have a few minutes left, I'm going to speed through this. But so I stands for interface segregation principle, right? Effectively, you should only depend on what you need, and the net result is that you should have then clearer code clearer code to understand and for execution. Again, with Hamilton, you write a Python function, it's declarative, it only depends on what it needs. Doesn't need on anything extra, right? So it's very easy to maintain. If you add other functions and you don't request them to be computed, Hamilton's not going to run it. So in the case here, if you have a really large pipeline, right, I don't have to, if I only want only one thing of this computed, so in this case, say a data set here, Hamilton's smart enough to skip computing this, right? And so very easy and clear then from a principle to understand what's run. D stands for dependency inversion, right? You should effectively avoid tight coupling between different parts of your code via abstractions. This is important if you want to ensure flexibility for the ability to change and refactor your code. Again, because Hamilton gets you the right functions. The abstraction here really is the name of the function and the input parameter types. And so everything in terms of functions therefore are pretty independent of each other. So they're pretty. If you can think of them as an independent iterable unit, it's pretty. As long as the name and the input and the type match, you can pretty change the implementation very easily. And then from a more macro level, right, you can group these functions into modules. And so if I wanted to refactor how I did feature engineering, I wouldn't have to touch data loading or model pipelines as long as I adhered to the abstraction of I need to provide the right functions that declare the right thing that can be output from this module with the right type. So to summarize the talk, hopefully I've imbued on you that Hamilton is a micro framework for expressing data flows in Python, and that if you write code with it, hopefully people won't be terrified of inheriting it. Hamilton paradigm itself, I think, helps increase software engineering best practices and therefore the value of your work by ensuring your code is naturally testable and documentation friendly. It helps you write more reusable and modular code, so you can actually move faster with your refactoring and as you're changing things. It's hard to do bad things, since Hamilton can provide you the safeguards to safeguard it, and that's because it helps standardize the way that you iterate and kind of add to a code base. And then one meta point from the talk is that, of the tools that we put out, how we design it actually can guide users towards, good software engineering practices. And if you were at the talk before mine, I think from the guy from Dexter, right, I think, a functional paradigm is hard to beat. And in which case, like, I think, Hamilton is another example of a framework that uses just the Python function as the kind of the interface that people kind of use. And so if you aren't going to use Hamilton, at least think about, giving people functions. Otherwise, I'm excited to mention I'm soft launching something with Hamilton where we're trying to enable people to more easily and quickly have things off the shelf. And so hub.dagworks.io is going to be a place where we're trying to curate these kind of flows that you can express with Hamilton to make it easy in 3 lines of code to download and have something up and running. And then otherwise, if you're interested in what I'm building on top of Hamilton, with the one-line code change, we can track versioning, lineage, catalog, and observability. So if you have these concerns, or if any of these capabilities are interesting to you, we'd love to chat with you. It's self-service, you can sign up for free. And then otherwise, thanks for listening. Hamilton's just a library, you can pip install, get started pretty easily. But otherwise, we'd love a star on GitHub. And yeah, thanks.
Any questions at table 1 upstairs on the 4th floor? Thank you.
Yeah. I feel like it was a pretty dense talk, and I speak quickly, so thank you if you managed to, to follow along. But yeah, happy to take questions, or I'll be upstairs at the booth.